last time was recursive ray tracing, so you hinted there might be something better.
Oh yes. So have you ever seen a video game trailer and gone, oh, wow, this looks absolutely groundbreaking, next level, I can't wait to play this. And then you play it and it looks something like that. Really not very good. The reason for that is because they pre-render these trailers. So they don't care how long it's going to take to render. They'll shoot out millions and millions of rays and use the best ray tracing or path tracing algorithms to render these really crisp images. But when it comes to real-time rendering, they can't afford that, and you end up with a result which looks not very good. So one of the ways that they can simulate really good light is with path tracing, and that's what I want to go over today. To really understand path tracing, we have to go back and quickly recap what we've done. So in previous videos, we spoke about ray tracing, which involves shooting rays into your scene, tracking where they go, and we compared it to rasterization and showed why that's better. And then we built upon that with recursive ray tracing, which is able to do reflections and refractions. And how that works is basically rays cooling themselves recursively until they terminate. Now, that's all well and good, but those all handle things to do with direct light. Now, one of the questions that I got on the previous video was to do with the shadow in the Cornell box scene. And one of the questions was, well, why is there something rendered there? It should just be black, right? And what I didn't go over was that you have something called an ambient value, which is basically a way of going, there is some light hitting it from somewhere. I'm not going to calculate it. I'm just going to say 10% of the light is just hitting it from somewhere, right? And in the first video, we went outside and it was a beautiful day. It was very unusual, actually. It was actually really nice weather. While this is more like the British weather. It's clouded over, it's been raining, it's horrible. But that's what we're used to, right? Now, if we were going to render outside using ray tracing the standard way that I originally said, we'd let's say shoot a ray off, it hits the floor. Right, let's check if what the light is. The light's occluded because it's in the clouds. Therefore, don't render any direct light. Therefore, everything outside would be one shade of light. Let's say 10 ambient value to 10%. Therefore, everything would just be grey. I mean, quite realistic actually for the UK. But in reality, that's not the case. What's happening is that the light is coming from our sun. It's bouncing around in the clouds, and then it's coming down, hitting different objects and then hitting our eye, right? And we can see in the actual clouds, there are some parts of the clouds that are more lit up than others because they're less dense, so more light is coming through. You probably won't be able to see this on the actual camera, but you know, you'll know what I'm talking about, right? So that's a form of indirect light, okay? But normal ray tracing doesn't account for that. You know, it just goes, right, some light will hit it from somewhere. But that really does hurt the realism of some of the images. If you're trying to render something that looks really crisp, it does affect it. So I want to draw the Cornell box scene, which is a scene that you create and render, and what you can do is compare other ray tracers and rasterizers and path tracers to each other because you're rendering the same scene. What I showed in the previous video was that we had a light source up here and there was a shadow here at the bottom of this square. The way it worked is because we shoot a ray out from the camera, it hit, let's say, this point here, we go, right, let's calculate the direct light, we shoot a ray off here, ooh, this square is in the way, therefore don't render any direct light. Indirect light is just a default ambient value of, let's say, 10%, therefore render 10% light on this floor, which is not black, by the way, it's white, but I can't draw white on here, so draw it as black. But yeah, now the issue is that it doesn't look super realistic, right? Because shadows don't work like that because there are some indirect light coming from anywhere in your scene. I want to show you what some indirect light may look like. So this is your light source. There may be some light bouncing off there and hitting there. There may be some light bouncing off like that. There may be some more up here. Or this can happen. There may be light going like this, hitting off like this, hitting off like this, and hitting off like that. It's coming from everywhere. How do we simulate that? Well, what we do is at the point that you're trying to render, you shoot off rays out into your scene that simulate the indirect light. So let me redraw this scene here. So I've redrawn this, and let's say we want to calculate the indirect light here. So what you do is you're trying to simulate light coming from everywhere. So coming from here, coming from here, coming from here, coming from here, an infinite amount of light. You can't do that. You can't shoot off infinite amounts of rays going everywhere. So what you do is you sample from those rays. So you can imagine that you have rays coming in from all around here. I'll draw it. There could be rays coming in from all around here, from this hemisphere here. So what you do is you, let's say, pick a certain amount of rays that can come in. So let's say we pick 5. So we'll pick 5 rays. We'll say, oh yeah, let's just shoot off one here. Let's just shoot off one here. Let's just shoot off one here, one here, and one there. Right? So these are almost like feelers. We're sending these out and feeling what the indirect light should look like. So we shot off those rays here. What do we do now? Well, we just render what the colour should be, right? As we normally would. So here we go, right, this colour is red, and there is nothing in the way, so we render it as a bright red. And we do the same for this one here. And here we've got, one green. Render that as a green colour there. These ones are blue, but they're occluded, so therefore you can't render any direct light here. But there is some indirect light coming in. I'll go into that in a sec. But let's just say it's a dark blue. Okay, imagine this is a dark blue. So, right, brilliant. We've sent those rays off and we've got the calculations that we need. So what is the indirect light? So what we do is we add all of these together. So we have red, red, blue, and green. And you add them all together and you divide by the number. This is Monte Carlo, where you're sampling from the amount of potential light coming in. So you add these all together, divide by the number, and you get the average amount of indirect light. Now, what I mentioned was that there's also indirect light coming into these parts of the scene, right? So what you do here, and this depends on what you set your depth to, i.e. the amount of bounces that you can do. So at the moment it's a depth of 1. Let's say you set it to 2. For these ones, you shoot off 5 more, like this. And you calculate the indirect light for this colour, right? And you do that again for this one. 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 And let's say you have a depth of 3. You also got to calculate the indirect light for the rays that you've just shot off there. So you calculate it for this one. You calculate it for this one. You calculate it for...
Presumably each of those rays, because there's so many more of them, is having less and less of an...
Yeah, that is true, yeah. So what you get is loads and loads of rays being shot off, right? But the more rays that you shoot off, the less those overall impacts of each ray has. And when you get to, let's say, a depth of 5, those rays aren't doing that much. The contribution is less and less. And you've got to remember, this is the indirect light for the indirect light for the indirect light for the... eventually, but it's not going to impact too much. But it is worth doing because it's just that nice shades that you can get, you know. So, yes, to summarise, it involves calculating indirect light by shooting rays out, seeing what colour they are, and then shooting more rays out for the indirect light for those rays, shooting more rays out for... And so you end up getting this bright... So it's like recursive ray tracing on steroids. It is a lot of rays, which is why this isn't really used for real-time rendering, because it's so intensive on your GPU. Now, all well and good me saying that, but what's the point, really? Does it actually look any better? I'm going to give you an example here of a situation where, yes, it really is useful for doing this. So imagine here we've got a scene of a corridor, okay? And you've got a camera. This can be your eye in this scenario here. And then we got a light source there. So if you were looking down a corridor like this, what would happen is that you'd see the end of the corridor here would be light, because it's lit up by this lamp or whatever. But it doesn't just stop being light there. It gets dimmer and dimmer and dimmer and dimmer and dimmer the closer you get to away from it, which makes sense, right? Because less light is hitting your eye. If you were going to rasterize or raycast this, what would happen is you get a very harsh shadow like that. And why would that happen? Because you shoot a ray out here, let's say hit, say, calculate a direct light. Oh, brilliant, it's lit up. But if you shoot a ray out here, I'll do that here. If you shoot a ray out here and calculate a direct light, oh, it's occluded by this part here, just set the ambient value as 10%. And the issue is that if you do that you can do that for all of these parts of the corridor, and they're all occluded, but there's no direct light hitting them, so they're all the same shade, and you get that really harsh shadow, and the lighting isn't realistic, right? And this is if you're going to rasterize it, or basic raycast or basic ray tracing algorithms, right? So what happens if we're going to path trace this? So you shoot a ray out, calculate the direct light as normal, no direct light. Okay, what about the indirect light? So what you do is we'll shoot out, let's say 5 rays, 5 samples. So you shoot out a ray here. And for context, let's say these walls are white, okay? You shoot out a ray here, 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 and shoot out a ray here, right? We just pick them at random, right? And what you get is you go for each ray, go, okay, is this in a direct light? Oh, yes, it is. So let's say this is white. Oh, yeah, that's in the light as well. Oh, yeah, that's in the light as well. Oh dear, these are not in the light. And this is with a depth of 1, so we're only shooting off 1 ray here. These rays are not shooting off more rays yet. But what you get is you get an overall light of white, or lit up, lit up, lit up, not lit up, plus, run out of space, not lit up. Divide that by 5, and what you get is 60% lit up indirect light. And let's say the indirect light makes up 30% of your thing. I'm not going to do the calculation, but that's how much light you render there for that part there.
I feel like I'm in Doom or Quake or something with like first person shoot 'em up.
Oh yeah, well that's This is the sort of thing I'm trying. I'd actually like to see a comparison. I think there is actually online between path tracing games like that versus rasterizing, and you can really see how far we've come. Right now, what happens if we're going to render this point here? All right, so we shoot out a ray as normal. We go, okay, is there any direct light? No, because it's occluded by this part of the wall. So what you do is you then shoot out 5 rays, right? Okay, let's add these together. So 1, check. Calculate lighting for this one. Oh yes, this is all good. Calculate lighting for that. Oh, it's just clipped the corner. Nope, that's not in the light. That one's not in the light. That one's not in the light. That one's not in the light. And so when you go to calculate the amount of light, it'll be lit up, plus not lit up, plus not lit up, plus not lit up, plus not lit up, divided by 5 equals 20% indirect light. Add that with your direct light, there's not a lot of light hitting there. But that's fine, right? Because that's how it would work in real life. Because less light, further down the corridor you get, less light is going to hit those positions from that light source there. And that's how you render those. It's not just a harsh shadow there, it's a gradient of the amount of light hitting there. That's what path tracing is trying to achieve. Global illumination, which is that light should be coming from everywhere, hitting everything, but more light hits certain parts of the scene than others. And it's all reflected and bounced around until and that's how you get those really nice images. Now, quickly before we move on here, this is with a depth of 1. What would happen is if you set it as depth of 3, that would shoot off 5 more to calculate indirect light of that. This one would shoot out 5 more. This one would shoot out 5 more. And then those ones that you shot off would shoot out 5 more, would shoot out 5 more. Even positions like here, which you've already calculated are in the light and have direct light, you still calculate the indirect light for these ones as well as the ones down here. And in proper scenes like the Cornell box, for the light, it isn't just black and white light, it is green light, blue light, red light, and that's where you get shades of light. If let's say we say the walls here are red down here, what you get is you'll get red tints up here because there's a lot of red light from the walls here, and you get really nice shading effects on there as well. All right, one thing I also want to talk about is how does it choose where the rays go, right? So let's say you have a surface here and you want to render the indirect light for this point here. So what really, light is coming in anywhere from here, okay? So what you do is just randomly choose rays along this hemisphere. So you can shoot one up here, one here, and one here. Rays that are closer to the surface here and further away from your normal will have less contribution to the overall indirect light. That is part of it, because if you have indirect light coming from that angle here, it's going to be less than if it's all the way up here.
Kind of less important, less prominent, right?
Yeah. So that's another part of it that you've got to consider. I've shown you why you use path tracing to render scenes like this. Now, should we actually have a look at a path tracer?
Let's do that.
Yeah. I'm showing you right now a comparison between OpenGL, which is a rasterizer, and a ray tracer here that I made. Now this is a framework that was built by University of Leeds. I've gone through this in the previous video, but now I want to show you what happens if we upgrade this ray tracer to a path tracer, right? So I'm going to give it a sample of 1, which means that for the indirect light, we only shoot 1 ray off. And let's say I think it's a depth of, let's say, 3. You shoot 1 ray off and see what happens there. I can tell you now, it takes a little longer because you're having to calculate that extra ray bounces from the indirect light. Right, it's finally rendered. Oof, that doesn't look very nice, does it? Because we're only shooting off 1 ray here for the indirect light, which means that it's not a very good estimation of what the indirect light really is, okay? So let's pick, it's probably difficult to see, but let's say we pick some on the floor. There's a lot of green and red scattered on the floor. Let's say we render this floor, shoot a ray out, hits the floor, calculate the direct light. It is direct light, but let's calculate indirect light. And what it will do, let's say for the red one here, it will go, right, pick a random ray direction. Oof, all right, it's over here. Shoot a ray off. Oh, it hits that red wall there. Therefore, the indirect light is red. That's not true though, because there's light coming from the red wall, light coming from the green wall, light coming from the white, light coming from the blue. It should be a mix of all of those things, not just one. Same with the green parts here, same with some of the blue colours on the wall there. It should be a mix of all of those colours because light is coming in from everywhere, not just one thing. So what you need to do is up the number of samples. So let's do 5. This could take forever. It's finally calculated and ooh, it's looking better now. Still a bit grainy, still a bit of noise, but in general it's looking a lot nicer. And what we're starting to notice is that along here, on this side of the square, there's a lot of green. And the reason for that is because there's a lot of indirect light coming from this green wall, and we're simulating that because we'll shoot rays out, and a lot of them are going over there in the green wall, right? Because we're now doing 5 rays, there is a higher probability that some of those rays are hitting that green wall, right? This is why we have more samples, and these rays are scattering out, and more of them are hitting the green wall. You can see there's still some, strange noise that colours going over because let's say 5 of them don't actually hit the green wall and they're going some crazy direction, right? However, if we then increase the sample to, let's say, 30, that should iron out most of the noise and we should get an actual real good indication of the amount of indirect light. Here's one that I rendered previously because I'm not waiting 3 hours for this to render. As I say, this is my path tracer that it's not the most efficient, but it does an all right job at showing you why we use path tracing. There is actually proper green shading here and red shading over here. And you can, if we compare, we've got the rasterizer on the left, and on the right we've got the path tracer. You can really see why rasterization just doesn't cut the mustard compared to path tracing, because the light is so uniform because we're not calculating any indirect light. We're using those ambient values that I spoke about. I've said how good path tracing can be, but I've only showed you my path tracer, which in the grand scheme of things isn't actually that good. I want to show you what an actual really good path tracer is and show you some of the things it can do. Right, so I'm on this is an article by Demo Fox, and they have a great little image here of a path tracer, and they've highlighted what is good about it and what path tracing does really well. So first thing, ambient occlusion, which is where if you're in a corner, there is less indirect light being able to hit the corner, right? Because there's this opportunity for light to come in. And you can see here it's darker. This area here is darker than, let's say, that wall, because less light is bounced around and being able to hit that part of the scene. Color bleed, and that's what you saw on my path tracer there, which is that light from the red wall. A lot of that is bouncing and hitting that object there. And you can see there's not much red here, because it's not there's less probability that light is coming from the red wall and hitting there. There's a high probability that indirect light is coming from there and hitting there. And I want to preface this by saying there are probably a lot of samples that have been used here, a load of samples. And this is going back to the thing I said about the video games at the start with the trailers. If they want to render stuff like this, they can do that, because this may take an hour to render. It doesn't matter because you're pre-rendering it all. But if you're trying to play a game real time, you can't really use really intense path tracing because your GPU just can't handle it. Maybe 10 years down the line, when GPUs get even better, maybe we'll start seeing proper path tracing used. And honestly, it probably is being used at some point. I just don't know about it because of how quickly this stuff moves. So if you want to render a scene, you've got to decide between the three methods. You can rasterize, which is very quick but can't handle complex lighting effects very easily. Ray trace, which is a bit of a middle ground. It's slower than rasterization, can create cool detail, but may struggle with really crisp lighting effects. Or you can use path tracing, which is a lot slower, but wow, does it look good. They're trying to say how much each ray contributes to the final light color. Now, imagine you're at the beach, okay, and you're looking at the ocean. If you're looking horizontally at the sea, you won't be able to see into the ocean. But if you then walk into the ocean and you look down,